And I will quickly introduce our speaker today, who is Sudhanshu or Dan, and he is a PhD student at University at UMass Amherst Theoretical Computer Science Group, where he is advised by Cameron Musco. His research interests lie at the intersection of machine learning and spectral graph theory. Prior to joining UMass, he studied computer science and engineering physics at Dartmouth College. And we're very glad to have him today. I'm also curious to learn more about your spectral graph theory work, which is also like a personal interest of mine. And one thing, as Farma posted in the message, so just for everyone, for next week, the reading group time will be adjusted since we have a speaker from Australia. So the time zone is quite difficult, like at this time for him. So for next week, the reading group time will actually be changed to 4 p.m. to 5 p.m. on Thursday. So instead of now, it will be like 5 hours from now, due to the time zone. So that will be a one-time change. Then we will go back to the 11 a.m. time. I think we have enough people to get started. Do you want to take the lead then?
Yeah, sure. Thanks for the introduction and thanks for inviting me. So I'll be discussing today this work on direct embedding of temporal network edges via time-decayed line graphs. This is work I did as an intern at Adobe with Ryan Rossi and some other mentors, as well as my advisor, Cameron Musco at UMass Amherst. And this will be a poster that I'll present at iClear 2023. Okay, so this work fits into this broader question that I've been interested in recently of whether deep learning is essential to effective learning on graphs. And by deep learning, I'm referring to the broader framework that's become very popular recently of nonlinearities, end-to-end backprop, and so on. So I became interested in this question after reading this paper, Simplifying Graph Convolutional Networks by Felix Wu and others at ICML 2019. And the specific question in this work, I would say, was, can we handle the most common graph benchmarks well without using deep learning? And they proposed a method that they find did actually work pretty well. So this inspired me to work on two kind of extensions I see of this. One to the heterophilous setting and the other to the temporal network setting that I'll discuss today. So I won't be discussing the second work, but I do want to start on a bit of a primer on this first work just to show my motivation, where I'm coming at this from. Okay, so let me discuss this simplifying GCNs work, which is kind of a prior precedent for what we want to do here. So the task in this paper was node classification using features, where you're given node features X and a graph matrix S. Specifically, this is a normalized version of the adjacency matrix. And given these two things, you want to make node representations X prime and some class predictions. So the vanilla neural network approach to this, where you don't use the graph, would be to take X, apply some linear transformation, and then some nonlinearity sigma, which could be ReLU, and then do this repeatedly to form the node representations, and then apply a softmax layer to get the class predictions. And now, how do we incorporate the graph into this? So if you're in a situation where you have a bunch of nodes, and you have some feature vectors on those nodes, generally the idea is if two nodes are linked, then they should be similar somehow. They should have similar representations, and ultimately they should have similar class predictions. So the way that we incorporate this specifically is we have steps where we kind of aggregate the feature vectors by taking by setting a feature vector of a node to the average over its neighbors. And it turns out to correspond exactly to multiplying by S. So this is kind of a useful thing to do if we eventually want the node representations as well as the class predictions to be kind of coherent and smooth across the edges. Okay, so GCNs do exactly this. They just multiply by S right after each of the linear transformations. Otherwise, it's pretty much the same as the vanilla neural network. And both of these learn these theta parameter matrices using end-to-end backprop using some of the class labels. Okay, so one thing to note about this is that it's kind of a feature learning method. And so this simple graph convolution paper that I found interesting asked whether this kind of complexity, this feature extraction is really necessary. So what they do is they get rid of all of the kind of deep elements, all of these nonlinearities, sigma, In that case, what happens is all these multiplications by s collapse into a single one by a power of s, and all these linear transformations similarly collapse into a single one. So this whole method kind of amounts to this handcrafted features where you take x and you smooth it across the graph, and then you apply a softmax layer. But because the input to the softmax is fixed, this is just logistic regression. So it's just this handcrafted smoothing followed by a logistic regression. And despite the simplicity and the interpretability of this result, of this method and the speed, it turns out to be as performant as GCN, at least on the common benchmark state test. So what we're looking for in this paper is there some kind of analog of this smoothing for static graphs that we can apply to temporal graphs? That's kind of the high level motivation. Okay, so let me get started with an example of something that we might want to do in temporal graphs. So I won't spend too much time convincing this this crowd that temporal graphs are useful, that they have applications or so on. So I'll just set up this example as something to refer to later. So we have in this example a few users, 1 through 4, and we have some websites, the green, blue, and pink websites. And each of these edges represents a click event or the idea that the user is interested in the website somehow. So in this graph, maybe the topmost edge represents that user 1 clicked on the green web page. So we have a bunch of these events. And what we're interested in is predicting whether user 4 might be interested in the pink web page. So in this example, if I'm a machine learning algorithm, maybe I realize that 1 and 2 are kind of similar, or maybe forming a cluster based on the edges we see, and 3 and 4 are kind of also forming a cluster. So since 3 was interested in the pink web page, maybe I would predict that 4 also is. Okay, but we want to care about we care in this talk about the temporal setting where there's a time attached to each of these visits. So maybe the visits we looked at were earlier on in the week, and now we have these 2 new visits that are later in the week, and we want to predict what 4 will be interested in later in the week. So again, based on the prior data we had, where 3 and 4 were interested in the same kind of web pages earlier in the week, since now we see that 3 is interested in the green web page later in the week, we might predict that 4 would also be interested in that web page. Okay, so again, I'm not going to spend too much time on all the different applications, but this is just setting up an example that we can refer to later. Okay, a little bit more formally, beyond that example, a temporal graph is a set of vertices, or I'm probably going to call them nodes, V, and a set of temporal edges, E. Each of these temporal edges is a tuple, UVT, which is a node, and another node, and then a time. For this talk, I'll assume that there are N nodes and M edges, which I think is the usual convention. And one thing to note is that the time in these temporal graphs is generally real valued rather than discrete, unlike the prior diagram where I had those early visits and later visits just for convenience. Of course, the discrete case, if we do have just these discrete values in the raw data, then that's kind of a special case of having these continuous values. Okay, one more thing I want to note before moving on is we can alternatively represent this data using what's called an incidence matrix and a time vector T. So I think the time vector is pretty straightforward. Just put the temporal edges in some ordering, and then just take each of those times and just lay them out in this vector. The incidence matrix, if you aren't familiar with it, it's a number of nodes by number of edges binary matrix. And I'll just explain it with this little example here, where we have these 4 nodes and these 4 edges. So what we look at in this, to fill out this incidence matrix, maybe the first row of it corresponding to the first node is which edges does this first node participate in? In this case, it's the first, second, and third edge, but not the 4th edge. So we fill it out based on that, adding 1s in the edges that it does participate in and 0s for the remainder. Another example would be 2. Nodes 2 participates in the first edge, but not in any of the other edges. So we have a 1 and then remaining being 0. Okay, so we can fill out the whole matrix like this. Okay, that's just establishing a bit of formalism. Again, I'm not spending too much time on this because I think most of you are familiar with this stuff. Any questions on this before I move on? Okay, so just as a quick review of some of the prior methods, these aren't the super recent methods, but I'm just selected 4 to get some breadth going. So I said I had a high level, a lot of these methods are kind of taking some high level static approach, some approach for static graphs and kind of applying a temporal element to it. So there's this CTDNE paper or method, which is based on temporal random walks. There's a lot of methods based on random walks for static graphs like deep walk or node to vec. And essentially all this does is it forces the random walks to respect time somehow. So they have to go forward in time along the edges. There's timers, which is based on SVD, kind of similar to the spectral embedding methods for static graphs. There's SteinGem, which is based on autoencoders, and there's Evolve GCN, which is based on GCN, as the name suggests. So I'd say there's, just to distill down what's been going on, maybe at a very high level, there's been a lot of deep methods proposed since Evolve GCN. And again, just maybe this is a bit reductive, but at a high level, what they do is they combine a graph neural network to handle the graph part and some kind of recurrent neural network to handle the temporal part. Okay, that's just giving a very brief overview of these prior methods. Okay, so what do we want to accomplish in this paper? Partly, we're responding to challenges when you're using the other methods. One challenge is they often require discretized time, even though generally the data in its rawest form is mostly tends to be continuous. So what this means is that these methods expect as input a sequence of discretized snapshot graphs. So if you want to use one of these methods, you kind of have to take those continuous times and bin them into a bunch of these discrete boxes to get this sequence. Okay, which is like an extra step you have to do. The other challenge maybe when using these other methods is that they generally return node representations rather than edge representations. So first, and maybe this is just my personal opinion, I think edge representations seem more natural when the basic unit of data in these temporal networks are these UVT tuples, where there's a time attached to each edge. But maybe, going beyond my opinion, more practically, when you have maybe the most basic tasks that you want to do on these temporal graphs are link classification and link prediction, which are kind of edge-based. So if you want to use a classifier, maybe a linear classifier on some vector representations to do these tasks, if you don't have edge embeddings, you're instead going to have to do what's called an aggregation of the node representations. So for example, if you want a representation for the potential edge from U to V, you will have to take the node representation for U and the node representation for V and average them and aggregate them somehow, for example, by taking the mean. So again, I think this just, it seems a little unintuitive, like an extra step to me. We don't actually have some theoretical work along these lines, but I think maybe there's some room there for something. Okay, so that's how we're responding to other methods, but what are the specific things that we want for this work? So I think the main things we're looking for are simplicity and interpretability. Maybe based on what I was introducing before, what we're looking for is the temporal graph analog of smoothing in SGC. Specifically, we want to understand what handcrafted features we can construct that yield good performance on the common benchmark. So this is the scientific component of this work. More practically, we want to introduce an easy to implement natural baseline that you can then go off from with more advanced deep methods. And one final benefit of having a simple method would be that we can do some theoretical analysis, maybe more so than what's possible with most of the recently proposed methods. Okay, but I'll discuss that later. Okay, so those are the high-level goals. And now how do we implement this?
Do you prefer to ask questions during the talk or after the talk?
Yeah, feel free to interrupt me at any point.
So just one quick question here. Do you think there will be like one reason why people like to use node embeddings is also because it's the most flexible representation? So it's difficult to go from edge embeddings to node embeddings. You can go the other way around. From node to edge, you just merge them. From edge to node, it's a little bit trickier. If you want to, let's say you have the edge embedding methods and you want to get a node classification task, it's a little bit less intuitive. And also, do you think there will be some representation difference in terms of like when you take a GNN and you want to generate a graph embedding, you would pull over the node embeddings. But if you have a bunch of edge embeddings, you can still pull over all the edge embeddings. But I'm not sure if theoretically there will be any motivation or in terms of how different the two representation would be if you do it on a node and edge level, or there's any difference at all. But it's just like something that I just thought of like as you were talking. Okay,
so maybe practically specifically to this temporal setting, if we look at the end result that we want, with a temporal edge, if you want the representation for it, it's kind of straightforward what exactly you're representing. You're representing UVT. With a node representation, maybe related to this point about discretized time, either it's a node representation for the node at all times, or you're kind of having to do a Cartesian product of nodes and discretized times. And then you have a representation for each of those. So I think that's the usual approach for the methods I compare to. That's kind of one point I'd make. And the other point that might apply to the GNN part of the question, the other thing I would say is, yes, it's true that it's pretty straightforward to take two node representations and aggregate them into an edge representation. But I'd say it's not that much more complicated to go from a a bunch of edge representations, a bunch of node representations can go to a, well, here, let me not get mixed up. A bunch of edge representations to a node representation. It turns out to just be, if I want a representation for a node, I just take all the edges it touches and I take the mean of them. So it's pretty much the analog of going the other way. It turns out to be exactly equivalent to multiplying by the incidence matrix also.
I see.
So I'd say they're pretty dual in that sense. I just think this is a little bit more natural, specifically for the temporal setting where you have a time associated with each edge. Because otherwise you're kind of having to discretize time in order to get a node representation at a given time, but there's not a time associated with the node itself. So I think that there's like this extra layer of complexity in that case.
Yeah. Thanks. I think that's that makes a lot of sense. Yeah, thanks.
Okay. So the very high level of the approach that we have is, as an analog of the smoothing in SGC, is to focus only on what we call the topological and temporal proximity of the interactions. So a little bit more specifically, what we do is we define an edge similarity matrix, which is an M by M matrix, and the ijth entry of this matrix, which corresponds to the similarity between temporal edge I and temporal edge J. It's going to have two pieces. So first is what we're calling this topological similarity piece, or topological proximity piece, which is just going to be the dot product of the corresponding columns of the incidence matrix. So if you think about this for a second, this term will be 0 if these two edges don't share a node endpoint. It'll be 1 if they share a single node endpoint, and 2 if they share both of the endpoints. Okay, so that's the topological piece. The temporal proximity piece is just a Gaussian decay based on the time difference between the two edges. So again, each edge has a time associated with it. If the time elapsed between the two edges is very long, then this decay will be going nearly to 0. If they're very close by, maybe the same time, then this term will just be 1 and there's no decay at all. Okay, so I introduced this as a similarity matrix, but if you ignore the temporal component, then this is a pretty well-known object. This is A is the adjacency matrix of the original network's line graph. And I'll give some pictures of this in a minute. The main extension we're doing is to go to this temporal setting, we're adding this extra Gaussian decay based on time. So that's the time decay piece, hence the name time-decayed line graph, or TDLG. Now, a few notes on this. Sigma t, first of all, is the hyperparameter, the only hyperparameter for this whole section that controls the rate of decay with time. So if sigma t is very high, then there's almost no time decay. If it's very low, then there's a very sharp time decay. If two edges are even a little bit apart in time, then the weight of the similarity element between them is decayed almost to 0. Another note is when you form the TDLG, what you're doing is converting a temporal graph with a node for each entry, for each entity, which would be a user or a web page in the example I showed before, to a static weighted graph, which has a node for each interaction. So this would be one of the click events of a user clicking on a web page. And this conversion is not lossless. It's giving up things like directionality of time and maybe some more complex structures like periodicity if there's an interaction that tends to occur every week or so. So this is kind of giving up some information, but maybe it'll be fine for the benchmarks anyway. Okay, so that was the formula picture. Maybe let's look at a real picture of what's going on. So we'll return to this example we had of users visiting web pages. Maybe let's just leave out time for now. We'll just consider the line graph component. So what we're doing is we're taking each of these interactions, like one visiting green, and making a node for it in this line graph. So this one green node corresponds exactly to this edge. We do this for all of the 5 edges in this original graph, and then now we connect them if they share an endpoint. So these two nodes, for example, are linked because they share the green web page. These two nodes are linked because they share the third user. So what's interesting now is if we have a link prediction problem in the original graph, like predicting whether 4 is more likely to visit the green web page or the pink web page, it becomes a node prediction problem in this new line graph. And because we know the rules for how a line graph, how nodes in a line graph are connected, we can form these kind of hypothetical graphs that would result from having these extra nodes. So now if I'm a machine learning method deciding whether this node or this node is more likely, it's just equivalent to deciding which of these two graphs is more likely. And maybe I would notice that there's 2 connected components in the original line graph, and only this 4 pink line graph is respecting that. So this would correspond to predicting that the 4th user is more likely to visit the pink web page. Okay, now adding the time element back, let's consider these 2 extra edges that occur later in the week that are dash dotted. Well, we can add these dash dotted extra nodes for them in the line graph and connect them as before if they share, based on whether they share a user or a web page, either of the node endpoints, and now we decay them based on time. So in this case, there's just going to be a decay based on if the edge goes from an early visit to a later visit. And now these edge weightings will be incorporated into whatever method we're using that takes advantage of the time-decayed line graph, whether it's a random walk-based method or a deep method or a spectral method. But we'll get into specifically how we use the time-decayed line graph in a bit. Are there any questions on this before I move forward?
Just very quick clarification. If you have multiple edges, so like if one edge shows up multiple times in the temporal graph, then only the most recent occurrence is preserved in this representation, right?
Oh, yeah, that's a great question. I actually meant to say that too. So if we had, for example, a second edge from user 3 to the blue web page, maybe later in the week, then we would just create a second node for it. So we wouldn't be throwing anything out. We would have if we have an edge from 3 to blue early in the week and an edge for 3 to blue later in the week, we have 2 separate nodes for them. And they will be decayed, they will be time decayed differently, right? The 3 blue edge that's later in the week will have stronger connections to these nodes. The 3 blue edge that's early in the week will have stronger connections to these nodes. So not only will we have a representation for both of them, if they occur at different times, then we'll have a separate representation that kind of takes into account the temporal prior.
That's interesting. And then does the blue nodes that's like repeated have connections with each other, like beyond the edges? Like
sorry,
so,
what do you mean?
So so you will just create a separate node each time an edge reappears, right?
Yeah.
Okay. And the nodes will have essentially the same, they will be essentially the same, except the edge weight is different.
Yes, so they're going to have connections to the same set of edges, to the same set of, let's call them interactions, just to be clear. What's an edge in the original graph, a node in the new graph. So if they're interactions involving the same entities in the original graph, then they will have edges to the same to the same interactions, but the weightings will be different, assuming that they occurred at different times.
Okay, I see. Okay. Thanks.
Right, yeah, thanks for bringing that up. That's an important point. Okay, so what are the tasks we'll look at? So there will be 3 of them. Maybe the most basic will be the temporal link classification task, where each temporal edge is associated with a class label. We're given some of the edges labels as training data, and we have to predict the remaining edges labels as test data. And then we have these 2 link prediction settings, what we're calling interpolative and extrapolative. So in both of them, we're given some real and fake temporal edges from some time interval T0 to T1. And then in the interpolative setting, we have to distinguish other real and fake edges from the same time interval. In the extrapolative setting, we have to distinguish real and fake edges from a future time interval. So this is maybe what's more traditionally thought of as link prediction, where you're given the past, you have to predict the future. This interpolative setting is maybe, it's not quite, but maybe more analogous to an anomaly detection sort of setting. But there won't be some parts of that setting where you have class imbalances and so on. Okay, in particular, the way that we're going to create these fake edges is we'll take the real edges, the U's, V's, and T's, and we'll randomly permute these columns U, V, and T independently. So what this does is it preserves the distributions of each of these columns independently, like the degrees of the nodes, both ingoing and outgoing, will be the same, as well as the time distribution. It won't be affected, but the correlations within the U, V, and T, the kind of structure in the graph, that should be destroyed. Okay, so those are the tasks. Now, how do we use the TDLG to do these tasks? So I'll start with the simplest task, temporal link classification. And I think we kind of use it, the TDLG, in the most straightforward possible way. So the first step is to form the TDLG of the network, which again is an M by M matrix. And pretty much what we'll do is we'll treat this first M as like the number of data points. So we'll treat the second M as the number of features. So the way we'll use it is we'll train a logistic regression classifier using the rows of this matrix as the input and the edge classes as the targets. Okay, now for temporal link prediction, where we don't have these classes, we're going to do something very similar, but with slight tweaks to each of these steps. So before we construct the TDLG, we'll have to add the fake edges to the network. And when we're training the logistic regression classifier, instead of those ground truth edge classes, we'll be using real edge or fake edge as the targets. Okay, now some things to note about this whole process. Because we're doing the super straightforward approach of just using the rows as the edge feature vectors, The feature vectors are very high dimensional and sparse. So their length number of edges, and they're very sparse because most interactions don't touch most interactions. Now, if we wanted, we could do some kind of dimensionality reduction to form the more traditional low dimensional dense edge feature vectors, and we'll also look into this in the empirical evaluation. Okay, the data sets that we'll evaluate on are these 5. So let me just go through what each of these are very briefly. So these Bitcoin data sets are data sets of Bitcoin users who rate each other as being either trustworthy or not. So it's the tuples in this data set are Bitcoin user I rated Bitcoin user J at time t as being trustworthy or not trustworthy. Escorts is similar. Let's say it's a network of buyers and rating sellers at given times of being either rating them positively or rating them negatively. WikiElect is a bunch of users of Wikipedia rating each other, voting on each other to either become moderators or not. And finally, ePinions, sort of like Bitcoin, is another who trusts whom network. One more note on these data sets is they range from small to mid-size to fairly large size. So over 100,000 edges and 100,000 nodes and 800,000 edges in the case of ePinions. And finally, some caveats on this. These are all social networks of some kind where these proximity priors are sensible. There might be different kinds of networks where these proximity priors don't make sense. I think that would be interesting to look into too. And the second caveat is that we won't be using node and edge features in this work. In other words, we're focusing on the transductive setting, but maybe the inductive setting would also be something interesting to look into. Okay, so with all that set up, now let's get to the results. So I've kind of presenting them in the most simple form where we're just taking, we're looking at each of the different settings, each of the different tasks, and we're looking at the mean AOCs aggregated across the data sets. So overall, what we find is that this TDLG method that we're proposing gives good performance across the three tasks, better than the methods we compare to. I will note that there are more recent methods that could very well be doing better, but we're not really claiming state of the art. It's more about the simplicity of the technique. So in particular, TDLG is performing significantly better across the three tasks on complicated teeth methods. And like I noted earlier, the TDLG are better than some of the compared methods. Okay, and if you're interested in the kind of results broken out and disaggregated across the data sets, that's also available in the paper. Okay, that's the performance. Now, how about the time? So it turns out that this method does pretty well on time, even though we aren't using a GPU for it, unlike some of the other methods. So this is a plot of the runtime, which constitutes one trial of learning the embeddings, then training a classifier on the training data, and finally predicting on test data. So across the 5 data sets, we're finding that this TDLG method is generally faster than the methods we compare to. Okay, so that's the performance and time. And how about the scalability as we want to go to higher and higher data sizes of data sets? So this was a common concern among the reviewers, which I think is quite reasonable. So everything in the TDLG method, it scales with the number of non-zero entries in the line graph. The line graph is a very big matrix, number of edges by number of edges. And if it were a dense matrix, then it would be way too big to work with. So we're really relying on the sparsity and the fact that there aren't that many non-zero entries. The number of non-zero entries in the line graph scales with the sum of squared degrees of the nodes in the original graph, which in theory could be quite bad. But generally, in practice, we find that it's not so bad, given that the degree distribution of most real-world networks is such that there's a lot of low-degree nodes and maybe just a few high-degree nodes. So due to this, it turns out that all the experiments we ran in this work were just fine on a standard 16 gigabyte laptop without a GPU. So in practice, it seems to work fine. Of course, if you do want to scale to networks with millions of nodes and millions of edges, you'll have to do something extra. So here are just a few ideas. One would be if there are entries of this TDLG that are already very small, for example, between nodes that are between interactions that do share some endpoint, but they're very far apart in time to the point that the time decay has made that entry almost zero, then you could just actually zero those entries out. So that's maybe the simplest idea. The second would be, again, recalling that we're kind of treating this TDLG adjacency matrix as, or the dimensionality of it as being the number of endpoints and the number of features. We don't necessarily need all M of these features. So we could just drop some of these columns. We could do it maybe randomly, or we could do it in a more principled way based on leverage scores or something. But maybe the most important of these possible extensions is there's no need to hold the entire TDLG in the memory at once. You can just compute the parts of it you need on the fly as you're training the classifier. So for example, if the classifier is taking a gradient descent step on temporal edges 1 through 100, because there's an explicit formula for what those entries would be, just compute those entries, use them for the gradient descent step, and then you can toss them out and keep going to the next 100 edges. So I think even though we didn't need any of these extensions for the scaling that we needed on the data sets we tested here, if we did need to scale to much larger data sets, I think there's room to do so. Okay, actually, that is the end of the empirical piece. Are there any questions before I briefly discuss the theoretical side?
On the computational side, so if I understand correctly, the worst case complexity, so the worst case, which is not going to happen, but the worst case complexity will be O(n) cubed, because your degree can be at most n, and degree square will be n square, and you are summing over the degree, so that means you can sum over n entries. Of course, that means a fully connected graph.
Right.
But that's likely never going to happen in real world graphs, but okay.
Yeah, exactly. So if you had the worst possible case of a fully connected graph, that would be order n cubed entries. But like you said, that doesn't tend to happen in real world graphs. Okay. And
the mini batch training should be actually much easier in this case, because because you can just sample like a block in your adjacency matrix. Well, not adjacency matrix, but the A matrix you have here, and then they will be independent from each other.
Right, exactly, because you have an explicit formula for each entry of the matrix.
Thanks.
Great. Any other questions? Okay, let me talk a bit about the theory work. So the main thing I want to highlight about the theory work is not that there are very interesting methods used or anything. I think the analysis is pretty simple, but it's more so that the simplicity of the approach allows you to do something very explicit and give a very concrete guarantee of what the method will do. This is in contrast to some of the more recent approaches based on GNNs and so on, where the theoretical analysis is mostly limited to is the model or is the neural network able to distinguish two classes of graphs? And these are results based on the WL isomorphism test, if you're familiar with that. But again, because our method is simple, maybe we can do something more explicit. So for the theory results, we introduce a certain kind of random graph model for the temporal setting, which is based on the stochastic block model. So this is a pretty famous kind of model for graphs in the static setting. So let me just explain the SBM if you aren't familiar with it. This graph on the left would be the adjacency matrix of a kind of the most basic kind of SBM. This is a graph on 100 nodes. The first 50 are in what we're calling the U community. The next 50 are in what we're calling the V community. And there's three possible kinds of edges, right? There's edges from U to U, edges from U to V, and edges from V to V. So in this most basic kind of SBM, there's a probability of an edge occurring within communities, meaning from a node in U to another node in U, or from a node in V to another node in V. And there's a separate probability of an edge occurring from a node in U to a node in V, meaning across communities. So in this case, there's a very high probability of an intra or within community edge, and there's a lower probability of an inter or across community edge. So that's what this adjacency matrix is. This adjacency matrix on the right would be an example of the opposite kind of case, where there's a lot of inter-community or cross-community edges and not so many intra-community edges. And generally, the task that we care about in the static setting with just the traditional SBM is you're given one of these adjacency matrices, and then you have to figure out which community each node belongs to. Is it in community U or community V? And of course, one thing is you wouldn't be given the adjacency matrix, in this permutation with the nodes already sorted into the correct order. There would be some random permutation. Okay, but that's again the static setting. So what we care about is extending this SBM to a temporal setting, and we introduce what we call the union of Gaussian timed SBMs, and it works as follows. So we make these two SBMs, what we're calling the early and late SBM. And for each edge in the early SVM, we assign to it a time in this early Gaussian distribution, which is in red. For each edge in the late SVM, we assign to it a time in this blue Gaussian distribution on the right. So hopefully it's clear why these are the early and late SVMs. Okay, now the way that we've configured these early and late SVMs is such that if you were to take the union over all of these temporal edges, what you would get is something with no pattern. The probabilities flip-flop exactly so that there's no structure whatsoever in the union of these two sets of temporal edges. So what this means is if you don't take into account the times of the edges at all, then there's no hope at all of you being able to take this adjacency matrix and back out the node communities from it. Okay, so since time is absolutely required, this is a good test case to test out our TDLG method. So as before, we take this data set, this random data set that we construct, and we find the line graph, and then we time decay it. So now for each of the M edges, we have an M-dimensional sparse feature vector. We can now project that down onto 2 dimensions using some kind of dimensionality reduction. In particular, we use the top 2 eigenvectors of the adjacency matrix. So this is a spectral dimensionality reduction. Now we have a point for every single edge in the original graph. And what the result is that the TDLG embeddings are roughly separating the 6 kinds of edge classes. And these 6 classes are, like I said before, you can have an edge from U to U, from U to V, from V to V, and you can have each of those kinds of edges in either the early or late time period. So these colors represent exactly those 6 edge classes. And again, these edge classes are roughly linearly separated in just the top 2 dimensions of the edge embeddings. Now, what we really care about is separating the different kinds of node classes, the U's and the V's. So for that, we need node embeddings. And like Andy had a question on this earlier, how do you compute node embeddings from edge embeddings? If you have a given node, you take all the edges that it participates in, and you just take the mean of those edges embeddings. So based on that, we can compute node embeddings. And it turns out that as we desire, that the 2 node classes U and V are exactly linearly separated in these node embeddings. So this is a good sign, but this is again just an experiment. I won't go into how we prove the theory results, but it turns out that with pretty simple counting arguments, you can prove that the TDLG tends to separate these 2 communities for all kinds of configurations of SVM that you could have, at least in a certain limit. Okay, so again, it's not the techniques that we find all that interesting. Again, they're pretty just simple counting arguments, but it's the fact that you can get a very explicit a summary of what the TDLG method will do on a given data set, which is generally out of reach with other methods. Okay, any questions on the theory result before I wrap up?
For the node embeddings, like it makes sense to just sum over the edge that are connected to it, but also you are only summing over one hop neighbor of the edge, like one hop edge of the node, if that makes sense.
Mm-hmm.
So it doesn't necessarily have information about like 2 hop neighbors. I don't know if that understanding makes sense.
Yeah, I agree. That's true. So I think in this case, when you do this edge embedding, when you do this dimensionality reduction, you're kind of considering global information in that case. You're as you do the spectral dimensionality reduction, that's what incorporates these multiple hops, and then that gets incorporated into the node embeddings. In the case of in what we were looking at before, when we trained the logistic regression classifier, that's also kind of when you train that weight matrix, you're looking at these broader neighborhoods. So that's where I would say the multi-hops get factored in.
Okay, I see. Thanks.
Okay, then I'll maybe wrap up. So as a summary, what we do in this work is introduce the time-decayed line graph, or TDLG, which is a simple and non-deep way of embedding temporal edges based on topological and temporal proximity. And we find this method to be fast, performant, and analyzable. I think there's a lot of future ways to go with this. 2 straightforward extensions are to the online setting, where you have streaming edges. So you have edges coming in real time, and you need to update the data structure, this TDLG, as well as the weights of the classifier you're using, like a logistic regression classifier, in an efficient way. You could also extend to the inductive setting. Like I said before, you could have a setting where the nodes in the training graph and the nodes in the test graph are on separate, potentially totally disjoint sets of nodes. In that case, you would probably need to incorporate the edge features or node features to do this classification or whatever test you're doing. I think this could probably be handled pretty straightforwardly by just combining the TDLG with some kind of inductive method for static graphs, but that would definitely be a future direction. And maybe the final one would be checking out some harder data sets where the performance is terrible without considering things that the TDLG throws away, like the directionality of time. So I think that's maybe just using this as a baseline is a nice way to determine that, okay, this is a hard data set where you definitely need to do something beyond the bare minimum. Okay, and maybe the broad final takeaway from this work is, while the deep methods, which are very popular recently, which do this automatically feature learning, are very flexible and very capable, I think also pursuing these more classical approaches where you are handcrafting the features, it tends to maybe teach you something extra because you have this transparency of what exactly a method is doing. So I think these are interesting to work on as more interpretable baselines for that reason. Okay, and I think I'll conclude there.
Yeah, thanks for the great talk. I have a few more questions, but since I've been asking questions all the way, so I will let the audience ask more questions first. Yeah, so do you want to go first, Sasha? And then you can go, Farma.
Yeah, sure. Thank you for your talk. It was very interesting. I guess I have questions about, so I think I was kind of checking out the paper and I saw that you mentioned that you could have another choice of the weighting for the time decay. So like the Laplacian weight decay, which I'm not exactly sure what that would mean, but you mentioned periodicity as something that wasn't included in one of the trade-offs with the weight decay that you have right now. Do you have some ideas of how could you see like periodicity being very relevant for the real world applications, and what are the framework for decaying the time you could adopt to account for it? I guess if you have ideas or thoughts on this.
Yeah, that's a great question. Thanks. So one example that I maybe referred back to is maybe you have some kind of event that occurs, every year or so. So if the graph was about people listening to YouTube videos or songs, it might be something like around Christmas, people start listening to that Mariah Carey song. I don't know what's it called, but so that happens every year. Maybe there are other kinds of structures like that happen, on a yearly basis, a monthly basis, a weekly basis. Maybe there are some kinds of meetings and organizations that occur every month. And the way that this is kind of throwing that away is because the time decay just happens based on the time period, you're not really looking at these periodic events. So maybe the most straightforward way to incorporate that kind of periodicity into the TDLG would be if you decide on a time period, like I care about yearly recurrence, then all you would have to do is just take this time difference, mod the period that you care about. So yeah, you would just look at the difference modded by 365 days or something, or 7 days or something. Does that make sense?
Yeah, thank you.
And do you have a question, Farma, or we can go to Kartik?
I think we can go to Kartik. I will ask next.
Okay. Yeah, you can unmute yourself, Kartik.
Hi, thanks Sudhanshu for a good talk. I have some question on this approach, or like a broad, more philosophical question. So you say that using such feature, like traditional approaches using where we handcraft our features and then use a logistic regression to do prediction is more interpretable and more simple baseline, but you still have to have some weights, right? I mean, you still have a weight in, for example, logistic regression. I was wondering, like, the way you are creating this graph, this line graph, using its similarity matrix, maybe can we use, like, if we use parameters here, for example, in the weight decay or in the time decay, or like if there are some parameters in this graph formation itself, so like where we are creating this, let us call it like latent graph for prediction. So if there are parameters here, then the performance would be better. But are you saying that, I mean, I expect the performance to be better, and I guess you would agree if these weights are learned in an end-to-end manner. But do you think that that would lose out on the interpretability to some sense? Or why would you not have parameters, basically? Moving our questions.
Yeah, I think that's a great question. So the way I see this is when you form this kind of line graph and you don't have parameters, you kind of know exactly what you are throwing away, right? Like I said, in this case, you know that you're throwing away the directionality of time, and you know that you're throwing away periodicity. If you added some parameters, maybe that allowed this to vary in a way that allows for periodicity to be learned, depending on how much you add, you don't know what exactly is being thrown away anymore. So that's why I see this as interpretable, because you know exactly what is preserved and what is thrown away. For sure, I think adding more parameters, if it results in a significant increase in performance, it's definitely worthwhile. I still think, you know, despite everything I'm doing here, I still think the deep methods are probably the way to go for most people, at least in this academic setting. I just think at the same time, it's interesting to have these kinds of methods where you know that there's significant restrictions on what they can do, just to see how much performance you can get on the common benchmarks. Because you know, if you have a deep method that does much better than this, you know it's doing something beyond this proximity. Maybe it's taking advantage of directionality or periodicity or something. So I don't know if that quite answers your question, but that's just how I reacted to it.
Yes, and like inspired from your approach, if one were to make a deep model, then I don't know. One direction could be that we use this. We create a latent graph before prediction. Would you think that helps? Because like we can just take these interactions and pass them directly onto a transformer or some kind of architecture where it learns some inherent relations between these interactions. Another approach would be to explicitly or like implicitly encode this kind of information into the architecture. And if you and from like your approach, if one were to get some inspirations, then since a simple approach like this can help, can give good performance, then we can just use it might be worthwhile to actually first encode, first create some kind of edge similarity matrix, and only then followed by a decoder. So like an encoder would need to create another line graph. I mean, if one were to create an architecture, then yeah, I mean, maybe one way where such interpretable baselines can help us in getting these priors that we need to encode in our architecture, in our deep architectures. Yeah, I feel.
Yeah, I totally agree. So the way that I see this, maybe as a piece of something that's probably a deep method or something, or you know, something more advanced, is I would return to this bullet point where all we're doing is we're proposing a way to take a temporal graph, which has a node for each entity, and create a static weighted graph, which has a node for each interaction. So the two things you could do beyond this are, first of all, you could, like you're suggesting, maybe have some parameterization where you're doing some variant of this. Maybe you're forming a TDLG which has some periodicity or something more complex. The other thing would be take the TDLG and now apply a deep method on top of it. So you could take advantage of edge features or node features if you're using a deep method and go to the inductive setting, but you do it on top of the TDLG as opposed to the raw graph itself. Yeah, so I guess that's one way I could see this used as a component of something larger and more capable.
Well, just another follow-up. So creating this static weighted graph, is this like, do you think it's like important or is necessary for, not necessary, but it's a good prior to learn representations? Or you can, the other way would have been to not create any graph, but directly use the interactions in like an RNN fashion or in like a sequential fashion, because the way we get these interactions are not, we don't really aggregate, we don't need to aggregate them in a graph to really encode these representations. But is there a motivation to why creating such a graph is would be important?
So I think the useful role of the graph is it's just to have a nice relational prior, usually, from what I can tell, as opposed to just using a pure RNN approach. So if the tuples that the node time tuples are in some strange order or something, as opposed to being localized in the topology of the graph, I think having a GNN component makes sure that you're propagating information along the neighbors properly. Yeah, besides that, I think the role of this, the TDLG, is when you have a node for each edge, I think it helps you learn edge embeddings as opposed to node embeddings as the fundamental unit. And I don't have any, great argument for why I think this is superior. This is just kind of an intuitive, this is just my intuition. So if you maybe accept the idea that learning temporal edge-based representations is superior, then I think this is another reason to use the TDLG as the basis for a method.
Would you say that the longer dependencies are also handled here, in a sense that there would be an edge? So if an interaction comes closer or comes early or comes very late, they both would be connected to each other if they have a common node, basically. So as opposed to in an RNN or a sequential learning paradigm where there would be one interaction would be decayed. I mean, there is a decay here as well, but there can be more forgetting in that case more than in this case. Maybe, although I'm not sure, because the Gaussian decay here could also be very penalizing, but it can be at least with sigma, it can be controlled, but of course.
Yeah. I'd say that's the main difference here. If you set the sigma t, you know exactly how much you're decaying, whereas in an RNN, there's probably all sorts of variables. I think people are still investigating what the memory of RNNs is and so on, and how it would interact specifically with these kinds of data sets. It's probably a very complicated question.
Yeah, thanks. Yeah, good talk. Thanks.
Yeah, thanks.
Thank you very much for the great presentation. It was very insightful. Actually, most of my questions have been already discussed. I just have one quick question. Have you considered comparing your results with some more recent GNN-based method, like TGN, for example, or Pint? They are definitely much more complex, but I'm just curious about how the performance would be different.
So we haven't done that. I think that would certainly be an interesting thing to look into. I suspect it's quite possible that they would outperform. I think the focus in our case was kind of getting the max performance per unit of complexity. So I think in that sense, probably this is the main point of the main strength of this work. But yeah, I think that'd be interesting. I can totally see these more recent methods outperforming.
Yeah, that makes sense.
So thanks for the great presentation again. I have one last question. So I'll just quickly ask, since we have 5 minutes left. So I think it's more on the general discussion side, more on the high level. So I think so far that I'm aware of, there are 3 different ways of converting temporal graph into some form of static graph. And then you go from there. So there's the ICML paper from last year on the equivalence of node representation in temporal graph. I forgot the exact name, but it's the time and graph and times n graph paper. In that paper, they essentially make all the edges into they flatten the entire temporal graph by having a time series for each edge. So each time there's an edge, you just add a indicator. So in that way, you have a static graph, but each edge have a time series. The second way is from the Pine paper, from the provably expressive temporal graph network paper, which they look at essentially converting it into a static multigraph. So between 2 nodes, you can have multiple edges indicating the edge at different time. And in your work, this is more similar to the second one, I would say. So in terms of like having like each edge where you have multiple representation of it in your static representation. So these are like three different ways that I'm aware of that converts it into a static representation. And I think so far it's unclear which one is the best way to go, or theoretically, if you learn from these three different representations, which one give you the best performance? Or if you want to do some sort of theoretical analysis, like the WL test from static graph, which one of those should you apply it on? That will give you like the most, the best setup for expressiveness framework. So I think these are like just in general, like a general discussion. So I don't know the answer to these questions, but I just thought it's kind of like all these three, like all another possibility is that they are all essentially equivalent. And there's not too much difference. But I guess in terms of the use case, maybe there are some subtle differences. So do you, like, are you aware of like these work? And
Yeah, at a high level, I guess responding to your point about the expressiveness, I'd say it's very likely, if I recall what these works were correctly, that TDLG is strictly less expressive because, like I said, we know that we're getting rid of some information like the directionality of time and the periodicity, whereas those they're kind of representing in a certain way, but they're preserving all the information still. The comment I guess I would make beyond that is, yes, this is losing information, but maybe it's the information that's preserved is preserved in a very simple way where you can just put it straight into a logistic regression classifier or something. Whereas, you know, in the time series representation, for example, it's probably a little bit more complex. It's not clear how to use a classical method to just do classification or something. So I guess there's maybe a bit of a trade-off there. But if expressiveness and theoretical guarantees based around expressiveness are the concern, that I think this is probably going to be more limited, and maybe there's something beyond this that needs to be done.
Yeah, I think that's a great point. And thanks for clarifying it. I think it's been more clear, and I think this representation is like works really well for the edge level, and it's more straightforward in terms of like how to design models to learn from it. So I think there's like a lot of potential here. And if there's no more questions, we can wrap up the talk for today. And if you have any questions, you can also like email me and then or then. So then we can have like offline discussion. And there's also the Slack group that you can send messages from. And let's thank Dan again for the great presentation and the very clear explanations. And then see you all next week at 4 p.m. EST.
Thank you very much for the presentation.
Yeah, thanks again for inviting me. Bye.
Bye.
Bye.